Today we shall start with the subject of rotation around a fixed axis. You can have a complicated body, but there is a fixed axis through it. Now we had the following formula. The total angular momentum derivative is equal to the sum of all the external torque. External torque this is the rate of change of angular momentum. This is a very important formula. We apply this formula to this system. Now, the axis, we look at the body. Now, the axis exerts, different parts of the axis exerts different forces on the body. So, suppose this is the axis. Let's say at one point, the axis, the axle, the axle exerts a force on the body. So let us say that it has two forces. One along the axis, one perpendicular to the axis. O is the origin. When we write this formula, we always first choose the origin, then write down this formula. Now, let O be the origin. X is a point on axle. And A and B equal to forces on the body by the axle. Axle 就是轴. Now we consider the z component of this equation. So we consider the right-hand side, the torque exerted on the body by A and B. The z component of the torque exerted by A and B on the body. Okay. R from O to X is upwards. That cross into A gives you something which is perpendicular to the axis. So A does not contribute. B is parallel to R. So B cross R is equal to 0. So both components exert no torque. A and B do not cause any torque along Z to the body. That's a trivial but very important conclusion. So that means all the points on the axle will exert force on the body, and therefore will exert some torque, but none of those torques is along the z-axis. So if you only consider this formula along the z-axis, then you can forget about any forces on the exerted by the axle. That means in this formula, if you only look at the z component, you only need to have all the other external forces. You can forget about the axle. Thus, when we consider Lz dot equal to the summation of R cross F I z component, we can forget about the forces from the axle. So this simplifies the problem. Okay, next I'm going to discuss a gyroscope. This is a picture that I enlarged from Feynman's book. It's in section 20, volume 1. It's a gyroscope. I'm sure many of you have played with a gyroscope. A gyroscope is a heavy wheel, and you make it rotate very fast, and then you put the one end of it on top of a tip. And the strange thing is that this thing, if it rotates fast enough, it would not fall. If you have something like this sticking out, if it doesn't rotate, it will fall down. But if it rotates fast enough, it will not fall down and it will perform a complicated motion like Feynman indicated here. We are going to analyze this, but not the complete analysis is rather complicated. But let us take a special case of it. Let's have this tip here, and we analyze. Let's assume that this rod is weightless. It's a very strong weightless. So, what are the forces on this body? There is a force going mg. There's a force from here, and there's a tension here. Now let us look from the top down. So this is the point, and this is the body. After delta t, it rotates into this way. It rotates an angle, delta theta. Let us take this point to be the origin. Originally, its angular momentum is along this axis. Afterwards, its angular momentum is changed. So L prime minus L, the absolute value of this is equal to this distance. This is the original L. This is original. This is the final L. So that difference is equal to L times delta theta. And that is equal to L times omega delta t. Let omega be the angular velocity around z-axis. We take this to be the z-axis. So in this diagram, the z-axis is upwards. So dl dt, the absolute value of dl dt is equal to L omega. In other words, in that diagram, we are talking about a simple case so that it doesn't have this motion. It just smoothly goes around in a circle. You can do that. You can make it go to that. And we are now talking about this angular velocity, capital omega. But what is this? This should be equal to the angular momentum, to the torque. Now, in order for the thing not to fall down, this whole system must suffer another force which balances this mg, and that force is along here. Now, but that force does not create a torque around O, because R is equal to 0 there. So the only torque is exerted by this mg. Now R is along this direction. mg is downwards. So R cross mg goes here into the paper, and that means it's exactly in this direction. So the magnitude of this is equal to, suppose this length is L, then it's equal to L times mg, right? The torque, this is equal to torque, and torque is equal to L times mg, because L is R, mg is the force, so R cross force is equal to L mg. So now we have a formula which relates omega to this. So we get the formula omega, the angular velocity, is equal to L mg divided by L. Every quantity is known here. Small L is the length of the rod, mg is the weight of the mass, capital L is its angular momentum. That depends on how fast you spin it. So everything on the right hand side is known. So you know how it would rotate. It would, in this case, go through a smooth motion. Now, however, if you start with and push it, if you don't allow it to go this way, you push it a little bit downwards, it will do this. It will do what Feynman indicates. But that's more complicated, because then you have to look at the angular moment. You have to look at the full equation, and it's complicated, so we're not going to discuss that. But this formula is already very interesting, because what it shows is that if you make the angular momentum smaller and smaller, that means if you spin it not so fast, then capital L becomes smaller. If capital L becomes smaller, omega becomes larger. So if you spin it less fast, it will go faster. Now, when does it begin to fall down? If it slows, if capital L is 0, thus omega becomes infinity. It will fall down. But let's analyze. In the previous argument, we have something which was not exactly right. It is that there are two angular momenta. One is this angular momentum, one is this angular momentum. And in what we have done is we have neglected this angular momentum, because you usually make a very heavy gyroscope, so this L is very large. So this formula is only true if omega is not too large. When omega is large enough such that this angular momentum become comparable with the capital L, this formula is no longer true. Now, what is the angular momentum? What is the angular momentum around the axis? It is equal to mL times L omega. L omega is the velocity. The angular momentum is m times r times the velocity, so it's equal to this. So the condition for validity of one is L omega is much less than L. Okay, if you write this formula down, it becomes m squared L cubed G has to be much less than L squared. That's the condition. So if L is too small, that formula is not right. In fact, that is when it will fall down. So what we just discussed is the principle of a gyroscope. A gyroscope has the strange property that if you try to push it downwards, it goes perpendicular to the way you want to push it. And that is utilized in the ancient days to stabilize something. If you have a very heavy ball put in a shell with no friction, then if you hold the shell and move around with it, the heavy ball inside remains in the original direction. That is how it becomes that has been used for various ways. In fact, for navigation. I think up to the 1970s, gyroscopes were used still in airplanes. But no longer. Does anybody know what is the modern principle of the gyroscope in those big airplanes? They have gyroscopes, but those gyroscopes no longer use this mechanical device. Does anybody know what is the new method? It's called the ring laser. Ring laser, we would not get into this, but it's one of the modern marvels. It's you create a laser beam which has, let's say, 4 mirrors. So if you send a laser beam, it comes back to here, and at this point you put another mirror in here so the laser beam would go this way. Now you send another laser beam which goes the other way. So 2 laser beams, one going clockwise, another one going counterclockwise. Eventually they interfere at this position. This is the fundamental principle of the ring laser. Now suppose you rotate it. When you rotate it, the ring laser going clockwise diminishes. Its number of phases diminish, while the one going the other way, the number of phases increase. So when they two interfere here, there is a slight difference, and that slight difference can be easily measured. But this is extremely sensitive because the wavelength of a laser is, let's say, 5,000 angstroms, and that's a very small quantity compared with this. So therefore, the laser's phase is an enormous number, and if you have a tiny difference between those two phases, you can detect that. So you can detect the angular velocity by the ring laser with very large accuracy. So the modern gyroscope really is just 3 ring lasers, one with axis this way, one with axis this way, the third with axis this way. And the phase difference of those 3 ring lasers are fed into a computer. And so therefore the computer can instantly tell you how much it has rotated. And that is the principle of the modern ring laser. This is the principle. I'm not an expert in it, but I'm positive the accuracy of that is something like more than 1 part in a million, or maybe even in a billion. So that shows the marvels of modern technology. Now we go into a new topic called the moment of inertia. It's also, the book calls it rotational inertia. But the discussion of the book is very sketchy. It's also very sketchy in Feynman's book because it has more algebra than in the usual textbooks. This subject is usually discussed in sophomore mechanics. We're getting into it because some people among you had written that the Professor Young's class is too elementary. So what we are going to do is somewhat more less elementary. And I hope many of you would learn something from these more complicated things. So what we are going to do is calculate the angular momentum of a complicated body. So you have a complicated body with many points, complicated rigid body, and we are going to calculate the angular momentum. The angular momentum is equal to summation mi Ri cross Vi. Now let us take the center of mass. Take this formula is true no matter where you take the origin. Now we take the center of mass to be the origin. So that L then becomes summation mi Ri cross Vi is omega cross Ri plus the summation of mi Ri cross velocity center of mass. We had a formula which gives the velocity. This now is the let me see. Let's write Ri prime, Vi prime as the this is the coordinate and velocity with respect to a stationary point, origin. I think I shouldn't say this. We have a Vi prime is equal to V center of mass plus R cross center of mass plus omega cross R, where R is relative to center of mass. So now I write this down. I write this part. Summation mi Ri cross omega cross Ri. Here Ri is relative to the center of mass. That by a formula that we have discussed is equal to Ri squared omega minus R dot omega R. That's A cross B cross C is equal to this. And I shall write this in the following fashion as summation of mi we are going to write interchangeably vector notation and matrix notation. Let's first investigate whether we understand this formula. This is a matrix. This is a square matrix multiplied by a column matrix. If you multiply it out, you get the three components become r squared times omega x, r squared times omega y, r squared times omega z, and that is precisely the components of this vector. So from this vector notation, I switch now to a matrix notation. The vectors all become column matrices. Now let's look at this one. This one is r dot omega times ri. If I multiply this out, you can read the first row all have x and then multiply by x, y, z. The second row has y and then y multiply x, y, z. The third component is z multiplied. If I now multiply this out, you see that because everybody along the first row has xi, so the product has xi, and that's why there's this r here. And this has y, this is z. So therefore, this multiplication automatically comes in this. If I make it even more clear, this matrix, this part is equal to this. This is omega. This is omega. This column is omega. This is x, y, z times x, y, z. This is omega. If you look at this, it's a column, row, column. But it follows the associative law. So therefore, you can first calculate this two. This two is nothing but the r dot omega. So this is r dot omega r, which is exactly this. What I just said in the last few minutes, please go through. This is elementary, but this is a trick which is repeatedly used. So what I'm saying is that this expression r square omega can be written in this form. This expression r dot omega r, automatically if I write this as r, this as omega, horizontal omega, this is r, then this automatically is r dot omega r. So I can write that in this form. So now I can write the total angular momentum is equal to summation mi times a matrix J, Ji times omega. Where Ji is equal to that square matrix, it's Ri squared, Ri squared, Ri squared. That's the first part, minus R, which is also a matrix. Does everybody agree with this? This is a column R. This is a row R. When you multiply a row by column this way, you get a number. When you first write the column, then write the row, you get a 3 by 3 matrix. And that's what this is. So now we have a Ji, which is a 3 by 3 matrix, which consists of two terms. One is diagonal. The other one is this kind of a matrix. And we now define a total J. A total J is equal to that square matrix. It's R I squared, R I squared, R I squared. That's the first part, minus R. total J is summation Ji. Sorry, I better have absorb the Mi into the Ji. So Ji is equal to Mi times this plus minus Mi times this. And total J is equal to sum of Ji. So every particle, this is called, Ji is called the angular momentum matrix, and as the moment of inertia matrix, moment of inertia matrix. You probably have learned in high school physics the concept of moment inertia, but that's too elementary. This is the more general moment of inertia. It's a matrix. It's sometimes called a tensor. A matrix is a kind of tensor. And we can write L is equal to J omega. If I write L as a column, then it is equal to a 3×3 matrix, which is the angular momentum matrix, moment of inertia matrix, multiplied by the column omega. Does everybody understand what I have been talking about in the last 15 minutes? Anybody is unhappy? Okay, so I assume everybody is happy. But it's complicated to deal with a 3×3 matrix. So we have now to simplify that matrix. So now we have to go to a little bit of a matrix algebra. J is a real symmetrical matrix. Why is the real symmetrical? Because J is this thing. And it's of course real. Every quantity is real. It's symmetrical because this is x, y, this is y, x. And of course it's symmetrical, x, z is z, x. So by definition, J is a real symmetrical matrix. Now a real symmetrical matrix, any 3×3 matrix has 3 eigenvalues. We have already talked about the concept of eigenvalue. So if I take J minus lambda I is the unit matrix, and take the determinant and put it equal to 0, that gives you a cubic equation in lambda, and with real coefficients. So therefore it must have 3 roots, and each root is called an eigenvalue. So any 3×3 matrix has eigenvalues. But we now have a real symmetrical matrix, and I want first to prove that all 3 eigenvalues are real. Lemma. All 3 eigenvalues are real. Does anybody know how to prove this? Okay. This is a fundamental theorem, and this is trivial, because if there's a lambda which satisfies this determinant equal to 0, that means there exists, by linear algebra, there exists a psi such that J psi is equal minus lambda psi. I times psi is psi is equal to 0. That is a fundamental theorem of linear algebra. If you have a determinant which is equal to 0, you can find a column which dotted into it gives 0. And that, of course, says J psi is equal to lambda psi. Now, we do not know whether lambda is real. In general, the lambda should be complex, so we cannot assume lambda is real. Now, if lambda is not real, then psi is also not real. So we don't know whether lambda and psi are real or not. But I can take psi dagger. I now introduce a concept of a dagger. A dagger, if I take a psi and dagger it, the definition is that you take the complex conjugate and tilde it. That means the psi, you first take the complex conjugate and turn it horizontal. So I now take psi tilde, psi dagger. Psi dagger is horizontal. Now, what is the psi dagger psi? Psi dagger psi is the sum of the absolute square of three numbers. If you have psi 1, psi 2, psi 3, psi dagger psi is equal to psi 1 absolute value squared, psi 2 absolute value squared, plus psi 3 absolute value squared. So this is real. And not equal to 0, because it's the sum of the three absolute values squared. If it's equal to 0, all three must be equal to 0. We of course are talking about a psi which is not 0, so this is not equal to 0. Now let us look at this psi dagger J psi. Psi dagger J psi is a multiplication of a row and a matrix, 3 by 3 matrix, and a column. Now they are, the matrix is of the form x squared, xy, xz, etc., etc. Let's look at the diagonal ones. So you have the first element times of the row times the first element of the column times x squared. And that's of course real, because it's x squared times something absolute value squared. So that's real. For the off diagonal elements, you have because it's symmetrical. One is xy, the other is yx, and what is multiplied is a complex conjugate of each other, added. So the symmetry of the matrix J dictates that this is also real. Is that obvious? Think about it for a few minutes. It becomes obvious. If it's still not obvious, I'll give you a formal proof. But the formal proof actually is also very simple, but it's better to understand it intuitively. Because psi dagger J psi, I'm now having a formal proof that this is real. This is a number. It's not a matrix. It's a 1 by 1 matrix, so it's a real number. So I can take its tilde. Now a 1 by 1 matrix, if you take its complex conjugate and tilde, the tilde doesn't do anything, because the 1 by 1, of course, after you turn it, is still the same thing. So this is merely the complex conjugate of that number. But by the rules of computation, first this is equal to psi I'm just copying down the definition. Now, J is real. Do you agree? Tilde is not changed. Psi star tilde starred, I just get psi tilde. J is real, so it's still J. This psi becomes psi star. But if I do this, and the rules for the tilde is to tilde everyone and reverse the order, so I get psi. Now J is symmetrical, so its tilde is equal to itself. And here I get psi tilde tilde, which is psi. So you see that this number is, after complex conjugation, tilde comes back to itself. But it's a 1-by-1 matrix, so that means it's complex conjugated itself, so therefore it's real. So this is a formal proof, but it's better what I explained earlier. You just write this out. If you write this expression out, you would easily see that the symmetry of J guarantees that it is real. Okay. Now the left side is real. Psi dagger psi is real and not zero, so I can divide. So that proves lambda is real. So let us have three eigenvalues. So I have J psi 1 is equal to lambda psi 1, J psi 2 is equal to lambda 2 psi 2, J psi 3 is equal to lambda 3 psi 3. Psi 1, psi 2, psi 3 are now real columns. And I can normalize them. Normalize them means I multiply the whole column by a number such that the absolute value squared of psi 1 is a vector. I now multiply it by number so that it becomes a unit length. So let psi 1, psi 2, psi 3 be normalized. Normalized means becomes unit vectors. So I now have three unit vectors, which are eigenvectors of J. Now I'm going to prove that they are orthogonal to each other. The three eigenvectors can be chosen perpendicular to each other. Proof. First, assume the three eigenvalues to be not equal. Assume lambda 1 not equal to lambda 2, not equal to lambda 3, not equal to lambda 1. In that case, let us take J psi 1 is equal to lambda psi 1, lambda 1 psi 1. I multiply it by psi 2 tilde. Then I take this equation J psi 2 is equal to lambda 2 psi 2. What I'm going through is a trick which is repeatedly done, and this kind of trick is fundamental to quantum mechanics. So you might as well learn it here. If I take this and multiply it with psi 1 tilde, I get these two equations. But I claim the left side are identical. Because everything is real. We have already said that. If I take the tilde of this, I get this. but it's a number. It's a 1 by 1 matrix, so if you tilde it, it's the same thing as itself. So therefore, these two are the same. So we have proven lambda 1 psi 2 tilde lambda 2 is equal to lambda 2 psi 2 psi 1 tilde psi 2. But psi 2 tilde psi 1 is equal to psi 1 tilde psi 2 because they are tildes of each other. So therefore, I get lambda 1 minus lambda 2 times psi 1 psi 2 tilde is equal to 0. We have just assumed that lambda 1 is not equal to lambda 2. So that means psi 1 and psi 2 are orthogonal. Are perpendicular to each other. Similarly, so all three of them are perpendicular. So psi 1, psi 2, psi 3 form an orthonormal system. And I can certainly change the sign of psi 3. So if psi 1, psi 2, psi 3 form a left-handed system, I just change psi 3 into minus psi 3, then it becomes a right-handed system. So form an orthonormal system, and I can add right-handed. But we have made the assumption that lambda 1 and lambda 2 and lambda 3 are not identical. You can ask what happens if two of them or three of them are identical. Then you require more considerations. But it's obvious that it must be true, because if you slightly change the j, if to start with two of them are identical, the third one is not identical, then I slightly change the original j, the three of them would not become identical, and then you have a system. Then you go to the limit that the two of them become identical, and still you have this orthonormal system. This kind of a situation occurs repeatedly. In other words, the existence of the orthonormal right-handed system is a general property, and the case of degenerate eigenvalues. If two eigenvalues are equal, it's called degenerate. The case of degenerate eigenvalues is a very special case, and in general, if you can prove it for the general case, then it works also for the limiting case of degeneracy. But we can even understand what we just said a little bit better. If all three eigenvalues are not the same, then psi 1, psi 2, psi 3 are uniquely defined by by what we said. If psi 1 is equal to psi 2, but not equal to psi 3, then you have 1 psi 3 and 1 psi 1, 1 psi 2, but these psi 1 and psi 2 are equal. In that case, you can rotate psi 1 and psi 2 and still can be eigenvalues. So as a consequence, in that case, if there is degeneracy, the choice of psi 1, psi 2, psi 3 is essentially not unique, because when all three of them are not identical, all three directions are fixed. But if two of them are not identical, you can rotate those two because they are the same. And if all three are identical, what is meant by all three are identical? That means j is equal to a. Then any vector is an eigenvector. So therefore you have a lot of freedom. Okay, now let us write this equation in the following form. We can write now we define, we have a psi 1, psi 2, psi 3. We call it gamma. Define gamma to be psi 1, psi 2, psi 3. We write the three elements, the components of psi 1 in the first column, the component of psi 2 in the second column, psi 3 in the third column. I get a gamma. Now, that gamma is a real orthogonal matrix. We have this concept before. Remember that maybe 2 weeks ago we discussed this. So gamma is an orthogonal matrix. Gamma tilde gamma is equal to gamma, gamma tilde is equal to 1. By definition, J gamma is equal to lambda 1 psi 1, the first column, lambda 2 psi 2, lambda 3 psi 3. And that is equal to psi 1, psi 2, psi 3 multiplied by because if you multiply those out, the first column is lambda 1 psi 1, second column is lambda 2 psi 2, third column is lambda 3 psi 3. So it's this. In other words, this is equal to gamma times if I now take the inverse of gamma, I get gamma tilde. Gamma and gamma tilde are inverses of each other. This is a fundamental theorem now. It is that if you have a real symmetrical matrix J, we have now found an orthogonal matrix gamma such that gamma tilde J gamma is diagonal. This is called diagonalization. I think I told you the story that at the beginning of the 20th century, there was a crisis in physics because Newtonian mechanics plus electromagnetism, which worked extremely well, created the puzzle that atoms should be unstable. Electrons in going around the nucleus would radiate, and therefore would continually spiral into the nucleus, and therefore all atoms should become unstable. All atoms should be emitting light all the time, and eventually should collapse. But that's, of course, that means the world would end. So that became a great crisis. And then people began to study, especially in Germany, because in those days Germany was particularly good in spectroscopy. So they studied spectroscopy and they found that the spectral lines have very strange regularities. And Heisenberg and Pauli were young graduate students, and they learned this and they tried to puzzle out what should be. They figured out many rules, but they cannot put them together into a theory. But by the early 1920s, when they were all in their young 20s, they realized that some sort of new mechanics was necessary. New mathematics was necessary. And this new mathematics was first dreamed up by Heisenberg when he was on vacation in a small island in the North Seas. But when he wrote a preprint and gave it to his advisor, not advisor, his boss, Max Born was some 15 years older than Heisenberg. Max Born was in his 40s. Heisenberg was his postdoc. So Heisenberg wrote this preprint and gave it to Max Born. Now Max Born was much more learned in mathematics, and he recognized what Heisenberg was writing down. In matrix notation, it's very simple, and that's how matrix got into physics. So later on, Heisenberg, Jordan, and Born wrote two papers. So they become one-man paper, two-man paper, three-man paper, and that founded matrix mechanics. Then half a year later, completely independently, under the influence of Einstein, Schrödinger didn't like matrix mechanics at all. He didn't believe in it. And he wrote down differential equations that became Schrödinger equations. And he then wrote 7 papers in 1926. It's an absolute marvel that a person could do so much. And in one paper, he wrote down wave equation, which is now known as the Schrödinger equation. In another paper, he showed that the result of these differential equations is the same as the result of matrix equations. And that equivalence between matrix equations and the differential equations is something that you will have to learn in quantum mechanics. So by the middle of 1926, people know that the essence of the solution of the puzzlement was there. It is that Newtonian mechanics cannot be applied to atomic problems. It has to be sharpened into a new mechanics, and that's called the matrix mechanics or wave mechanics, or later together it's called quantum mechanics. And so if you become very familiar with what we are discussing here, it'd be very easy for you to accept many things in quantum mechanics later. Now we have that equation, so now we write it. We have that, so we can write it as J equal to I just move the gamma and the gamma tilde onto the other side. Therefore, L is equal to J omega. J is a square 3 by 3 matrix, omega is a column. And this is equal to gamma, lambda 1, lambda 2, lambda 3, gamma tilde, omega. But we had earlier discussed, when you multiply gamma tilde onto a vector, you are merely looking at that vector in a new coordinate axis. So gamma tilde omega is equal to omega prime. Omega prime is equal to components is equal to vector in a rotated coordinate system. So this equation becomes gamma tilde L is equal to lambda 1, lambda 2, lambda 3 times omega prime. But gamma tilde operating on any vector is equal to, so this is equal to L prime. What does that say? That says that in the new coordinate system, in rotated coordinate, rotated by gamma. After you rotated, the three components of the new vector omega prime is related to L prime by a diagonal matrix. That means L prime 1 is equal to lambda 1 omega prime 1. L prime 2 is equal to lambda 2 omega 2. L3 is equal to lambda 3. Because this is a diagonal matrix. If I call those new three axes, the three axes, all this is about in the center of mass system of the body. So there are three new axes. I call them E1, E2, E3. E1, let E1, E2, E3 be the three unit vectors along psi 1, psi 2, psi 3. So this equation merely means L is equal to lambda 1 omega 1 prime times E1 plus lambda 2 omega 2. So these are all dots. Sorry, these are all dots. L dot is equal to j omega. So no. Forget I was confusing myself. No dot. We have not dotted yet. So L is equal to lambda 1 omega 1 prime E1 plus lambda 2 omega 2 prime E2 plus lambda 3 omega 3 prime E3. That's a fundamental formula. Let's review what we have learned. The system, this body around the center of mass has the three axes. These are called principal axes of inertia. So any solid body around the center of mass has three principal axes of inertia. Around each axis of inertia, there's a lambda 1, lambda 2, lambda 3. Actually, usually one calls it I1, I2, I3. So from now on, we are going to change notation. We no longer call them lambda 1, lambda 2, lambda. We call them I1, I2, I3. These are the three principal moments of inertia. And if a solid body rotates, it has an omega. We have proven that before. Now let's look at that omega in the coordinate system where you take these three principal axes, and these components will be called omega 1 prime, omega 2 prime, omega 3 prime. In the future, we also are going to drop the prime. But anyway, it has so that the direction of omega and the direction of of L are not necessarily the same. We are going to change this notation and write it this way. So here's omega. and there are three. You resolve it into three components along the three principal axes of inertia, and then you multiply the components by I1, I2, I3. If I1 is equal to I2 is equal to I3, then omega and L are parallel, because L is equal to I1 times omega. But if the three of them are not all the same, then omega is not in the same direction as L. So L would go in that direction. So this is the thing which makes rotation more complicated. In linear motion, P linear momentum is equal to m times v. In linear motion, P is equal to mv. P is the linear momentum. V is velocity. Now, so therefore, the linear momentum is always in the same direction as the velocity. So, P and V. P and V are different concepts. V is a kinematic concept. P is a dynamic concept. P has mass in it. But they are always parallel to each other. Now we have omega. Omega is the generalization of V from linear to angular. But the strange thing is that omega and L are not parallel, are not necessarily parallel. They are only parallel to each other if I1 is equal to I2 is equal to I3. And that lack of parallelism between omega and L is what makes angular motion sometimes very complicated. Is everybody happy so far? Okay. Now we have a lot of theory that we have to be more familiar with what's going on. So let us now talk about moment of inertia, about principal moment of inertia. So I have many bodies, many points, and this is the center of mass, and there is three principal moment of inertia. Each particle contributes something to the moment of inertia. We are now talking about this in the center of mass system. So the contribution is, we have written this as mi times xi squared, xi yi, xi zi, yi xi, yi squared, yi zi, zi yi, zi xi, zi yi, zi squared. And when I sum it, let's forget about the off-diagonal elements. Let's only look at the diagonal elements. The diagonal elements is summation xi squared. This is summation yi squared. This is summation zi squared. So, sorry, that's the second term in the angular momentum has, this is the second term. This is something I don't care. But the first term is mi times ri squared in the diagonal. So therefore, mi's contribution to J, to the total angular momentum, is mi times ri squared, ri squared, these are all zeros, minus mi times xi squared, yi squared, zi squared, something, 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 something. So now let's just concentrate on the diagonal. Ri squared minus xi squared is equal to yi squared plus zi squared. This is xi squared plus zi squared. This is xi squared plus yi squared. Something, 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 something. Now I don't care what those something are, because if you sum it, you know the result is diagonal. So all this junk would eventually cancel each other out after you have summed everybody out. So we now know I1 is equal to summation mi yi squared plus zi squared. I2 is equal to summation mi zi squared plus xi squared. I3 is equal to summation mi xi squared plus yi squared. By the way, in physics, we usually write these three formulas. CP means cyclic permutation. So you write this equation down, and then you permute it cyclically. Cyclically means x becomes y, y becomes z, z becomes x. So if you use that by cyclic permutation, you get these two equations. So what does this equation mean? It means that if you choose the principal axis, you must first say that before you can proceed. If you choose the principal axis and this is the x-axis, then I1 is equal to the sum of m times the distance to that axis squared, because that's yi squared plus zi squared. That I'm sure is exactly corresponds to what you learn in high school physics. The angular moment, the moment of inertia about the axis is equal to sum of mi times the distance to that axis squared. So this is correct. But what we now have is that this is only true if you choose the three principal axes of the inertia. Around another axis is a very complicated thing. Because of this, we have a formula. Let us take I1 plus I2. I1 plus I2 is equal to summation mi yi squared plus zi squared plus summation of mi zi squared plus xi squared. So that is equal to summation mi xi squared plus yi squared plus 2zi squared. And that's clearly bigger than I3. So we know that the three principal axes of the inertia satisfy the identity I1 plus I2 is greater than equal to I3 and cyclic permutation. What that means is that I1, I2, I3 form a triangle. Any three numbers, any three real positive numbers satisfying this kind of equation means that they can form a triangle. Now, let us consider a cylinder. Let this be the z-axis. This is its center. Is it obvious that the z-axis is a principal axis of inertia? Obvious, because for every point here there is a diametrically opposite point, and if you add the xi, zi, if you add the off-diagonal element of the contribution of this point, you have a point A, and I call it A prime. The point A has a mass. It contributes to J. The point A prime contributes to J. If you look at it, you will see that A and A prime have the same Z, but equal and opposite X and equal and opposite Y. Right? It's X, Y here. That's minus x minus y, but the z is the same. So if you put that into the J equation, you will see that the z component, the contribution of A and A prime is such that here's something, these two does everybody agree with this statement? This term is the contribution is Zi-Xi, but this term is the contribution is Mi-Zi-Xi. But Mi-Zi-Xi for A and for A prime are equal and opposite because they have the same mass, they have the same Z, they have opposite X. So if you add, is equal to 0. So what the A and A prime contribute to J, the contribution to J of A and A prime would cancel each other. So these are 0. This is something. That, if you think about it for a while, that means that the Z component, the Z-axis is one of, because it's already diagonal. The diagonal means that the J in that coordinate system is I1, I2, I3. All the off-diagonal elements are 0. But we have already proven that these off-diagonal elements are all 0. So therefore, that shows that if you now diagonalize this one, that's enough. So therefore, the z-axis is an axis of inertia. So for a cylinder, the z-axis is always a principal axis of inertia. But how about the x and y? The x and y would be perpendicular. And since it's cylindrically symmetrical, you can arbitrarily choose. Because that is the case where I1 is equal to I2. And the principal axis of inertia, E1 and E2, are perpendicular to each other but are not absolutely defined. You can choose any two perpendicular axes and they would serve as they can serve as the principal axis of inertia. So is everybody happy with what I just said? The net conclusion is that for a cylinder, one knows that there is one principal axis of inertia, and the other two you can choose arbitrarily perpendicular to it. But how about the magnitude? Okay, first, let's take this long cylinder. Let's take this pen. I3 is along this direction, and it's equal to summation of xi, yi. If it's very thin, xi, yi is very small. What is the I1? I1 is axis, say, this way. And the distance of many points on the tensor to that axis is very large. So would you agree with me that that shows that I3 is small and I1 is large? So in this case, a thin cylinder, I1 is equal to I2 is bigger than I3. So if I draw the triangle, I get I1 is equal to I2 is equal to I3. Now if I compress it to a very small disk, let us flatten it. Flatten the cylinder. That means compressed into a thin disk. So now it's a disk. I3 is this way. So it's I claim it's equal to the principal axis of inertia is summation of R squared, because it's x squared plus y squared. While I1 is the sum of x squared. I2 is the sum of y squared. So I3 is equal to I1 plus I2. Does everybody agree with this statement? This is a disk. By definition, this is the z-axis. So it's summation mi xi squared plus yi squared. That's I3. Take this axis, I1. It has only sum of y squared. Take this axis, it has only sum of x squared. So I1 plus I2 is equal to I3. And I1 is equal to I2, so they are equal to half of I3. So if I draw this, it becomes like this. This is I3, this is I1, this is I2. So for a long cylinder, it's a triangle like this. For a flattened cylinder, it's a triangle like this. In the middle, there is a configuration where I1 is equal to I2 is equal to I3. It's obvious that if you have a sphere, I1 is equal to I2 is equal to I3 because it's completely symmetrical. But I1 can be equal to I2 equal to I3 without being a sphere. That means it's a cylinder. Okay, I assign exercise to you. What is the shape of the cylinder for which I1 is equal to I2 is equal to I3? Find the cylinder for which of course you have to define it's a uniform cylinder. It's with uniform density for which I1 is equal to I2 is equal to I3. Let us now. I think we have absorbed too much mathematics. Let us now come to reality, to a situation. I'm sure you have all seen in stage shows, 杂耍. You can have a girl standing on a disc, and the disc rotates. The disc rotates very fast, and if she holds two heavy yarlin, you all know that if she does this, what happens? She would spin faster. That's elementary according to what we say here, because let's assume she is a cylinder. So her angular momentum in the z direction is equal to I, the moment of inertia in the z direction, times omega in the z direction. And so when she moves the yarlin, the dumbbells, closer to herself, it's clear that the I becomes smaller, because I is equal to summation mi xi squared plus yi squared. So they become smaller. If I becomes smaller, because L dot is equal to torque. She suffers no torque in the z direction, because what she suffers are only vertical forces, and vertical forces cannot cause a torque in the z direction, because two vectors parallel to each other gives you a cross product which is zero. So she has no torque in the z direction, so therefore Lz dot is equal to zero. That means Lz is equal to a constant. So when she stands on the platform and rotates, her total angular momentum in the z direction is not changed. In other words, this is a fixed quantity. So when I decreases, omega increases. That's the reason for that motion. Okay, we will have more to say about the rotation of rigid bodies, and I want to remind you that there's going to be a quiz, a midterm, next Monday.